Welcome. My name is Mahesh Kakade. This is the course on algebraic number theory. This is the first lecture of algebraic number theory. In this lecture, I will give you an overview of the course, what the main goals of the course will be, and we will start with a few definitions, and then next lectures will prove some theorems. Okay. So, what is the goal of number theory? So, aim of number theory is solving Diophantine equations. So, if you have not seen what Diophantine equations are, these are polynomial equations, i.e. polynomial equations in one or several variables with integer coefficients or sometimes rational coefficients for which we seek rational or integer solutions. Okay, so that's so this is loosely speaking what Diophantine equations mean. They are polynomial equations in one or several variables in which all the coefficients are integers, and we want integer solutions for these equations. So, let us look at some examples. Perhaps the most well known example is Pythagorean triplets. So, you want x squared plus y squared equals z squared, right. We learn this for right angle triangles, that square of length of two sides is equal to square of the hypotenuse, and it is a natural curiosity to ask when such a right angle triangle will have integer sides. Okay, so, we have several solutions to this, for example, 3, 4, 5, or you double it 6, 8, 10, etc. So, so given a Diophantine equation, you can ask several questions about it. So, questions about Diophantine equations. First question you can ask is there a solution? Okay. So, this question may have answer yes, or it may have answer no. If it has answer yes, then you can ask how many solutions are there. Now, of course, this question can have several meaning. You can ask if there are finitely many solutions, you can ask if there are infinitely many solutions, you can ask if there how many solutions there are up to certain modulus, etc. And if you can answer second question as well, then you can ask a stronger question: can you find all solutions? Again, this question can have several meanings depending on what you mean by finding all solutions. Okay. If there are finitely many, can you give an algorithm that will stop in a certain number of steps to find all solutions? If there are infinitely many, then is there a good way of describing all those solutions, etc. And so, we can go back to our example, or we can look at other examples. So, for instance, if I look at x squared plus y squared equals 3z squared, you can ask if this has any solutions. Of course, an equation like that will always have solutions 0, 0 and 0, x equal to 0, y equal to 0 and z equal to 0. But we want non-trivial solutions. So, at least one of them is non-zero. In this case, that will force two of them to be non-zero. So, in this case we can easily prove that there are no solutions. So, no solutions. And how do we do that? Well, this does not require any algebraic number theory as such. We just look at this equation modulo 3. So, consider this equation modulo 3. So, we get x squared plus y squared is congruent to 0 mod 3, and you find solutions of this equation modulo 3, and the only solutions are x congruent to 0 mod 3 and y congruent to 0 mod 3. Okay. So, we can write x as 3 times a, y as 3 times b, and if I plug this in the equation, I get 9 a squared plus 9 b squared equals 3 z squared. If I divide everything by 3, I get 3 a squared plus 3 b squared equals z squared, which implies that z squared is divisible by 3. So, hence 3 divides z squared, hence 3 divides z, and you can write z as 3 times c. So, I get a squared plus b squared, or I had 3 there, right. So, 3 equals, if you go to the previous page, you have 9 c squared. Yeah, but anyway, I mean whatever this is, if you had a solution a, b, c. So, if x, y, z is a solution and D is GCD of x, y, z, then x by d, y by d and z by d is a solution with GCD equal to 1. So, we can always assume that, so such solutions are called primitive. So, such solutions with GCD equal to 1 are called primitive solutions. So, in this case we can always assume that x, y, z was a, so we can assume x, y, z is a primitive solution okay, and then we proved 3 divides x, 3 divides y and 3 divides z. That is a contradiction. Which means that there is no solution. Okay. So, in many cases it is easy to prove that there is no solution, but in lots of cases it is very hard to prove that there is no solution. So, here is a famous example. You take x to the n plus y to the n equals z to the n bigger than or equal to 3. So, very famously Fermat conjectured, or he thought that he had a proof to show that this has no non-trivial solution. So, this has no solution in which x, y, z x times y times z is not 0. Okay. but of course, we do not know if he really had a solution or not, and this was proven by Wiles in 1995, more than 300 years after Fermat asserted this. So, that there are no solutions with x, y, z not equal to 0. Okay. So, this is famously very hard to prove. It uses lots of machinery from various parts of mathematics, not just algebraic number theory, algebraic geometry, analysis, etc. Okay. Another example where it is not very easy to prove that there are or to find all solutions is x to the n plus 1 equals y to the m. So, you want one integer power to differ from another integer power by exactly 1. Okay. And so, there is one solution to this, 2 cubed plus 1 equals 3 squared. Okay. And at least if you want x, y to be positive, then you can show that there is no other solution. So, this was conjectured by Catalan and proved by Mihalescu in around 2005 or 2002, I think. So, 2002 Mihalescu. So, this is the famous Catalan's conjecture. Another example that I would like to give is Euler conjectured that. So, again as a generalization of Fermat's assertion that there are no solutions to x to the n plus y to the n equals z to the n if n is bigger than or equal to 3. Euler considered a1 to the power n plus a2 to the power n, so on up to a n minus 1 to the power n minus 1 to the power n. So, he considered n minus 1 nth power and asked if this is equal to an nth power or not, and he conjectured that again this has no non-trivial solutions, but this was proven to be false. So, this was Euler conjectured that there are no non-trivial solutions. Okay, and this was proven false by Elkies. He actually found an example, and this was not done by brute force, but using a lot of sophisticated mathematics. So, he proved that if you take fourth powers of these three numbers 1, 5, 3, 6, 5, 6, 3, 9 to the 4 plus 1, 8, 7, 9, 6, 7, 6, 0 to the power 4, then this is 2, 0, 6, 1, 5, 6, 7, 3 to the power 4. So, you can check this on a computer that it works, but it is not easy to find this if you do not know this. Anyway, so he disproved Euler's conjecture. So, these are the sort of problems that one encounters in number theory. But what is specifically algebraic number theory about? So, in algebraic number theory, we not only consider Diophantine equations and integers, we also consider extended number systems. So, field extensions of rational numbers. Okay. So, let me define what a field is, and then I will try to motivate why we need to consider to go beyond rational numbers or go beyond integers to solve Diophantine equations. Okay. So, I do expect familiarity with field theory, Galois theory and abstract algebra, but nevertheless I will try to define as many things as I can, but as a prerequisite for this course you should know abstract algebra, Galois theory and field theory. So, what is a field? A field is a tuple k with addition and multiplication such that, so 1 k with addition is an abelian group and k minus the additive identity, so which we denote by 0, is also an abelian group. And there is a distributive property. So, A times B plus C is same as A times B plus A times C for all A, B and C in K, right. So, this is what a field is, and of course, the familiar examples of fields are you take real numbers with addition and usual multiplication, or you take complex numbers with usual addition and multiplication, or you take rational numbers with usual addition and multiplication, or maybe somewhat less familiar is you can take z mod p z with usual addition and multiplication. Here p is a prime number, or analogous to the construction of complex numbers from real numbers, you can take Gaussian numbers q I. So, this is all a plus I b such that a and b are both rational numbers, and here I square is equal to minus 1. Okay. So, you can check that this also forms a field with the usual addition and multiplication. Okay. So, these are some of the examples of fields, and here is a definition. So, characteristic of a field K is the smallest positive integer n such that if you add 1 to itself. So, let me say such that 1 plus 1 plus 1 equals 0, and this is taken n times. Okay. So, the smallest n for which this happens, this is called characteristic of K, and it is denoted as this, and of course, such an n may not exist. So, if such n does not exist, then we say that K has characteristic 0. This may seem counterintuitive. You may want to define it to be infinity, but the convention is that this is said to be characteristic 0. Okay. So, again to give you examples, characteristic of real numbers is 0, characteristic of complex numbers is also 0, characteristic of Gaussian integers or Gaussian numbers is also 0, characteristic of z mod p z is p. Okay. So, it is positive characteristic. All right. So, so what are number fields? Our main object of study object of study in this course are number fields. So, what are they? I will recall all these definitions more systematically in the next class, but this class is just about motivation of algebraic number theory. So, let me quickly give you the definition. Number fields are finite extensions of rational numbers, and since I am assuming familiarity with field theory, I can assume you know what this means. These are finite extensions of finite field extensions. So, finite field extensions of rational numbers. Okay. So, again let me give you some examples. Qi is a number field, okay, and the degree of Qi over Q is 2. But for example, R is not a number field. Okay, or complex numbers is not a number field. Okay. Similarly, Z mod Pz is not a number field. But more generally, as a generalization of Gaussian numbers, you can have the following thing. You can define zeta n, zeta sub n to be e to the power 2 pi I by n. Okay. So, zeta 4 is I, it is one of the possibilities for taking I, right. So, this is an nth root of 1, this satisfies. So, zeta n to the power n is equal to 1. Okay. I can take the number field q zeta n. So, this is all summation I going from 0 to n minus 1 a I zeta n to the power I, such that a i's are all rational numbers. Okay. This is a number field. So, q zeta n is a number field, and we will study these number fields in great detail in this course towards the end of this course. These will be our primary examples of number fields and various calculations that we do. So, these are called cyclotomic fields. Okay. Because zeta n is a point on unit circle in complex numbers. Okay. So, this is a field, and now let me go back to Diophantine equations and tell you why we look at these number fields. So, consider our example x to the n plus y to the n equals z to the n. I can rewrite this as y to the n equals z to the n minus x to the n, and I can factorize this as product I going from 0 to n minus 1 z minus zeta n to the power I of x. Okay. So, you can check that this factorization is valid, but this factorization takes place in q zeta n. Okay. All right. So, you have product of certain numbers here as a as nth power. Okay. So, you have n numbers here whose product is y to the n. Again we can assume that if you have a solution of x to the n, y to the n plus y to the n equals z to the n, then we can assume that it is a primitive solution. We can divide out by the common divisor of x, y and z and assume that their GCD is 1. Then we may hope that on this side all these numbers that we are taking product of are co-prime in some sense. Okay. And if they are co-prime, if product of co-prime integers is an nth power, then each of those integers should be an nth power. So, we may hope that these things are themselves nth power and then work from that and get a contradiction. So, this was the attempt in 19th century made by several people to prove Fermat's last theorem this way. It does not quite work because firstly we should define the notion of what an integer means in this number field. That can be done. So, that led to all these developments in algebraic number theory in the 19th century, precisely the attempt to prove Fermat's last theorem using number fields. Okay. The most important reason why this does not work is unique factorization fails in these number fields. Okay. So, let me write down what I said. So, 19th century attempts to prove Fermat's last theorem tried to use this factorization and somehow the person who went the furthest is Kumar. He proved that if p is a prime number and it is odd, if unique factorization, so we will learn all these terms in the course. Unique factorization holds in this ring Z zeta p. So, I did not define this, but you can imagine what this is. Instead of having rational coefficients, you take integer coefficients. Again, we will look at all these rings and we will see what the significance of these is. If unique factorization holds in zeta p, then x to the p plus y to the p equals z to the p has no solution with x, y, z not equal to 0. Okay. So, Kumar was the person who went furthest. He proved that if unique factorization holds in this ring, then he can prove Fermat's last, that case of Fermat's last theorem. Okay. Now, the curious thing is, so you can ask whether this ring always has unique factorization. Okay. One can ask that question. Unfortunately, it happens that this is not the case. This ring unique factorization does not always hold in this ring, and again it was Kumar who did a lot of work in this direction, and we will study much of his work in this course. So, that the failure of unique factorization led to the concept of ideal class group, and that will be our another main object of study in this course, studying ideal class group, proving that it is finite, getting algorithms to calculate ideal class group, etc. Okay. Nevertheless, this approach of using bigger number systems than rational numbers to solve Diophantine equation, although it started in a very specific way with Fermat's last theorem, it has been extremely fruitful, and I hope I convinced you that it is good to look at number fields. So, these are the objects that we will study. We will not talk much about Diophantine equations in this course after this lecture. It is good to keep that at the back of your mind, that that is our main motivation, to find solutions to Diophantine equations. But the course will be mostly about studying number fields, sub objects of number fields like rings of integers, unit groups, ideals in number fields, finding prime ideals in number fields, finding ideal class groups of number fields, etc. Okay. So, this first lecture was motivational about why we want to study algebraic number theory, and I already defined for you what a number field is. From the next lecture we will look at actual definition, properly look at definition of number field and consider various objects related to number fields.